Hello, my name is Ali Hamza and I'm here with my partners Ali Tahir, Sayed Anas and Mohammad Asad to present our final project for CS412, Traveling Salesman Problem. Essentially, the problem is an optimization problem. The idea behind it is that it is about a salesman who has to travel to an n number of cities where he only has to visit each city only once and then return to the original city. We can reduce this problem to the Hamiltonian circuit problem. That is an essential problem in graph theory. This is not to be confused with the problem of finding an Hamiltonian circuit within a graph, as those are different. The problem is NP hard. The exact brute force solution for the algorithm for the problem runs in a time complexity of O of n factorial. And that means that you have to find out each path, each Hamiltonian circuit within the graph, and then traverse it, and then figure out whether it's the most minimum path or not. The design techniques we've decided to use include two types. We have the exact solution and we have three approximate solutions. The exact solution uses the algorithmic technique of design of dynamic programming, and the approximate solutions use various techniques and approximations to find out a very accurate solution to the problem. The methods of empirical analysis that we've used include an implementation in Python of the most bare bones implementation of the program, which may or may not include other efficiencies that have been introduced by Python libraries and the language itself. We've then ran the same algorithm on the same graph multiple times and then averaged out their. I'm going to now explain the held Karp algorithm, which is the exact algorithm for finding the optimal Hamiltonian circuit in a complete graph. We use dynamic programming in this by exploiting the property of the traveling salesman problem, which states that every subpath of a path that is the optimal path is also of minimum distance. This algorithm allows us to speed up from O of n factorial to O of n squared to the power n. As we can see, this is a substantial speed up, as according to the Stirling approximation that approximates the growth rate of the n factorial, we can see that we are reducing our growth from n to the power almost an n to the power n function to n square times 2 to the power n. We should also note that this only works on complete graphs because our algorithm finds optimal Hamiltonian circuits, and if one is missing, then the algorithm may not work. We begin with a 4-vertex graph that's connected completely. As we've discussed, we need to look at every subpath within the graph. So we start from the smallest path and then we build up to the largest. As we can see that this is similar to taking a power set of all the vertices, and we can do that, and this results in 2 to the power n subsets. However, it's easier to visualize this idea with a tree, so we will do that. When we use a tree, we can begin at the lowest level, and if we are at A, then we need to check where we are coming to A from. So basically we need to check all these child nodes and check what is the previous vertex. So if we're coming to A from D, then we are at level 1. This is already a minimum path if the entire path is a minimum path. So we will then move up to level 2 and check where we're coming to D from. And we must do it for all child nodes. So when we reach B, we'll see that now we have two subpaths diverging from the path from the node B. And here we'll pick the minimum path between the two paths. As we reach the source node, we'll be able to pick the most optimal path just by solving the same problem of picking the minimum path over and over again, which leads us to a very elegant solution, elegant cost minimization function that starts us off at any source vertex I and takes the entire set S of all vertices, and then it picks the minimum shortest path by adding the cost function of the time of some vertex I that and some vertex k, and then we move back to the vertex k and check where we're coming to the vertex k from. Overall, this function has a time complexity of n squared 2 to the power n. The reason that is because we have 2 to the power n subpaths, and we have to check on each subpath the vertex we are at. We have to check each vertex on every subpath, and
The next approximate solution that we are going to look at is the pairwise exchange method, also known as the two-opt method. Let's say we have this graph and we try to find a Hamiltonian path using the nearest neighbor approach. What we see is we get a solution that has a total weight of 29. What we can decide to do is improve upon this path and find a path that has a total weight that is lesser than 29. If we try to exchange some of the edges in this graph, what we find is we can in fact come up with a better solution. So this has been an improvement over the path that we got from the nearest neighbor algorithm. So how do we go about doing these exchanges in the edges? Let's say we choose two edges in this Hamiltonian path. Let's call this edge U and let's call this edge V. And these vertices will be called U1, U2, and these two will be called V1, V2. While choosing these edges, we have to make sure that the two edges do not share a common vertices. Now we delete these two edges and we get two disconnected graphs. Now what we do is we join U1 with V1 and U2 and V2. These are these. When we take the sum of these two new edges, this turns out to be 12. The sum of the older edges that were deleted was around 18. We compute the difference of these, and if the difference turns out to be negative, there has been an improvement in the total weight of the Hamiltonian path, and therefore we decide to preserve the new edges. Having looked at that, it becomes easy to follow the algorithm that actually implements the pairwise exchange method. First of all, we initialize an arbitrary path, we set the best variable equals to that arbitrary path, and we iteratively improve upon the path best. How we do that is we use two loops in order to iterate over all the possible vertices and take all the possible edges that we can delete and exchange as we did in the earlier slide. This statement ensures that the two edges do not have a common vertices. Once we select two edges using these two loops, we exchange those vertices with the new vertices using the same method that we used in the earlier slide, and we compute the difference of their sum. If there is an improvement in the total weight of the graph, we decide to swap the edges permanently. Otherwise, we keep iterating over it. So we can see that the two inner loops, the first one takes O of n minus 2, the other one takes O of n minus 1. So the each iteration of the while loop takes around O of n squared. But there's a problem over here. The while loop only stops until there is no further improvement in the path. So what has to happen is the total weight of the edges of the path has to converge to a value such that there is no further improvement. So what we are doing until that point is we will keep going on and try to find all the possible edge exchanges that we can do. We get another path and we try to do the same with that new path, and we look at all the possible edge exchanges that we can do to it. So this is practically just an exhaustive search through all the possible solutions of a Hamiltonian path, through that Hamiltonian path. So theoretically, the time complexity of this solution is again O of n factorial. So, but why do we care about the solution then? Well, there's a good news. In practical situations, the solution converges quickly in real life applications.
Nearest neighbor is one of the solutions to the problem of DSP that finds an approximate cost of traveling from a point and returning back to the original point. We will find out why we call this problem an approximation. So what is the nearest neighbor problem? A salesman starts from a random city and visits the nearest unvisited city until they are visited and returns back to the starting city. So the algorithm starts by choosing any starting vertex, and whenever you reach any vertex, we look at the weights of all the edges that lead to the vertices we haven't visited yet, and we choose the one that has the least weight. Then we repeat this step until we have reached the last vertex, or else we go back to the starting point. The nearest neighbor is not optimal. This is because if we look at the brute force approach, we get an accurate answer. Brute force calculates the total cost of each Hamilton circuit and returns the minimum out of them. Hamilton circuit is a circuit where it travels to every vertex only once. As it can be seen that the cost of brute force gives us 23, whereas in the nearest neighbor, even if we start from any of the vertices, we still end up with the cost that is greater than 23. However, nearest neighbor is efficient because it does not require to traverse through all the possible edges. Instead, it uses the least weight, whereas brute force calculates all possibilities, which takes up about n factorial. So nearest neighbor is n squared because at each point we need to find its nearest neighbor, so that is n. And computing the distance from one point to all the other is n. Hence, total is n squared. These are the references, and thank you.
Lastly, we will look at the Christophidis-Suryukov algorithm. Before we go and get into that algorithm, let's look at a two approximation algorithm for finding an approximate DSP tour. This algorithm finds a minimum spanning tree for the graph and then does a DFS-based walk of it, and then returns a Hamiltonian cycle. This is an big O of V square algorithm, and it has an approximation ratio of 2. So we can improve this algorithm to get a more accurate result by adding a few more graph operations. Let's look at those operations in the next few slides. So we have a graph that whose edges, the weights of the edges obey the triangle inequality. Therefore, they form a metric space. So first, similar to the first algorithm, we find a minimum spanning tree, and after that, we find a set O which has all the vertices in T which have an odd degree. And since we know by the handshaking lemma that the number of vertices with odd degree is going to be even, we know that we're going to get an even number of vertices. And then we can find a subgraph that is induced by those vertices by the vertices of O on G. And then we can find, because we know that the number of odd vertices is even, we can find a perfect matching, and we can also find a minimum weight perfect matching using a particular algorithm. And then we will do a union of the matching and the spanning tree, and we will form a Eulerian multigraph. After that, we can simply calculate an Euler circuit. Since we know that the Euler circuit is going to have repeated vertices, we remove those vertices, and then we find a Hamiltonian circuit. And we know that that circuit will exist because the graph is complete, which means that whatever vertex we remove, we know that if we can find an edge to the next path, we can find an edge to the next vertex because the graph is complete. So let's quickly look at the analysis for this algorithm. We know that we know that the complexity of this algorithm is O to the power big O of V cube. This is because the most expensive algorithm in this is finding a minimum weight matching, which is achieved through Edmonds' Blossom algorithm, which was published in 1965 or so. This algorithm is a 3/3/2 approximation algorithm, which is an improvement compared to previous algorithms because it gives a constant approximation ratio, and which means that the cost of this tour, the approximate tour, is not going to be more than 1.5 times the cost of the optimal tour. So let's quickly go over the comparison of all the algorithms we've discussed. So the uninteresting naive brute force approach will obviously yield a result with time complexity big O of n factorial. Other than that, we discuss the Karp algorithm, which is a dynamic programming algorithm which will have a complexity of big O of n squared times 2 to the power n. Then we discuss the nearest neighbor algorithm, which has a complexity of big O of n squared and an approximation ratio of big O of log n. And then we have the pairwise exchange, which has a complexity of, in the worst case, exhaustive search will be big O of n factorial, but it usually converges, so it's still an efficient algorithm. And it has an approximation ratio of big O of square root of n by 2. And lastly, the Christophidis-Surikov algorithm has a complexity of big O of n cube and an approximation ratio, a constant approximation ratio of 3 by 2, which makes it among all the algorithms, the most efficient approximation algorithm. And it has been so since 1976 until very recently in July, a better algorithm was discovered.